So for the last few videos, we've been playing with simple transmitters and the high voltage regulated power supply, the Heathkit PS3. Now, people have been asking about possibly a solid state version of this power supply. Solid state, high voltage regulated, very useful for simple transmitters like 1 and 2 tube crystal controlled breadboard transmitters that you might be building. Also, the free-running oscillator, the self-excited oscillators such as the Hartley and this TNT transmitter that we've been using on 80 meters, these really benefit from a highly regulated power supply. Now in the old days, they would use a very heavy-duty transformer, some type of a tube rectifier, and they would use oil-filled capacitors, a gigantic choke, and a stiff bleeder resistor. If the power supply was capable of several hundred milliamps, then the small drain of a transmitter like this would not cause regulation issues. Today, we like to be a little bit more efficient with switching type power supplies, but we know that switching supplies can introduce some noise into the system. So I think we should do a linear project. Let's build a linear high voltage power supply, and let's make it variable. So something maybe between 0 and 250 volts, 0 and 300, 0 and 400, something like that. And it better be able to supply upwards of 100 milliamps for these small transmitters. Now, I can't guarantee that it's going to be as fancy as the Heathkit supply as far as the circuit complexity goes. It will be simpler, but we will have better regulation than the Heathkit was able to supply. I'll guarantee you that. I'm going to get into the parts next, but we have to have a working schematic to start with. We'll develop a parts list and then get some of the parts on order. And there'll be some breadboarding along the way to improve the regulated supply. Let's just realize that this thing is going to be a part of your test bench. Build it nice. Don't put it on a piece of wood, something that's going to end up at the flea market with question marks and people saying, "What is this thing?" Or recycled in your junk box. Make it a nice package. Maybe it's an enclosure, a nice box, nice metering, digital or analog, both okay. Or maybe a box like this with a nice front panel. So next, let's talk about a schematic and parts.
I'm not going to get into bipolar or MOSFET transistor theory. We can do that another time, and there's plenty of that stuff on the internet. We're going to talk about high voltage linear regulators. These can be made with bipolar or power MOSFET transistor pass devices. As a linear regulator, either type can be used in simple voltage follower type regulators. These will accurately maintain a target output voltage over a fairly large current range. So we will be building what we all recognize as a DC follower circuit. So beyond high voltage specs, a high GM or transconductance part is an important part of the device characteristics that we're going to be looking for. You can use either type of device, bipolar or MOSFET, but modern metal oxide semiconductor field effect transistors, or MOSFETs, are more common nowadays. Even though these devices are optimized for fast switching, switch mode power supplies, Class D amplifiers, and so on, they can be used in the linear saturation mode as a follower. Many are optimized specifically for fast switching, so using them for linear power service at high dissipation, you better be derating them, perhaps cutting the dissipation by 50%. For linear low voltage, high current supplies, like you remember those old brown Astron supplies, bipolar still reigns supreme. So I talked about linear saturation mode. What's linear saturation? What are you talking about, Mike? Is it linear or is it saturation? We're used to devices either being in the ohmic region, where they're linear like a variable resistor, or fully on like a logic-controlled switch. But there is a third mode. This third mode is when you're in this follower condition. This is where the device is biased into saturation, and it acts as a constant current source that follows the gate to source bias voltage. Taking a look at the MOSFET, when we have a voltage between the gate and the source, current will flow from the drain to the source. There's 3 regions to understand with the MOSFET. Really 4 regions. First, cutoff, where the gate to source voltage is so low that the drain to source impedance is high Z. That's cutoff. Second, the linear ohmic region, where the device acts like a resistor under the linear control of the gate to source voltage. And there's a nonlinear region where it starts to get into saturation. The device acts like a nonlinear resistor in that area. And finally, we're in full saturation, where the device acts like a linear current amplifier with a voltage gain just under unity. This is where we're going to be operating the device as a follower. For a MOSFET pass element to function properly in this linear saturation role, it must constantly satisfy the saturation condition that VDS is equal or greater than VGS minus V threshold. What's V threshold? It's the threshold or the minimum gate to source voltage required to create a conduction channel between the source and the drain. We sometimes call this the overdrive voltage. Since VDS always exceeds this overdrive voltage, the drain current ID is nearly independent of VDS, and it's primarily a function of the gate voltage alone. During linear saturation mode, the MOSFET operates in a saturated state or in the saturation region, and it behaves like a gate or voltage-controlled current source. Contrary to what happens when fully on or fully enhanced, the drain source impedance remains relatively high, resulting in high power dissipation. In any linear mode, the power is given by the product of the drain current and the drain source voltage. So this is ID times VDS. And these are both high at the same time. That means heat. This requires a device with good transconductance or gain. Remember, this is the gain of the device. Ideally, we want zero impedance output on our regulator so we can drive any load. R out approximately equals 1 over the transconductance value of the MOSFET. Operating in any linear mode, saturated or not, it's going to demand very good thermal management, overcurrent protections usually required, and so on. The controller is a voltage that we introduce from the gate to the source. We're going to make this controller variable, but based on a well-regulated reference voltage. It's a Zener stack with a potentiometer. The problem with this type of regulator is that the power efficiency of the device is proportional to the drain to source differential voltage. Therefore, the power dissipation increases in proportion to the output to input voltage ratio. There's two types of controllers for the gate. The open loop type, which we're going to use, it's a simple voltage divider. This type of regulation is based on the ability of the device to maintain a constant resistance over load, current, and temperature. Because modern MOSFETs are usually optimized as DC switches, and bare source follower gain is strictly less than 1, and it varies with load and there's other losses, they can be a bit unpredictable in linear operation. The more complicated closed-loop feedback type uses an error voltage that samples the output voltage at the load to influence the control voltage in order to more closely maintain a constant voltage at the load. I am hoping we don't have to go that far. So in review, our open loop regulator, we're going to be using a MOSFET as a pass voltage follower, a source follower, is a buffer circuit where the input voltage is applied to the gate and it sets the output voltage at the source. It provides an extremely high input impedance and a low output impedance, making it ideal for isolating sensitive control circuits, like our potentiometer, from the heavy current load. The drain is connected to the power source. The gate draws near zero current, but it defines the source voltage. To maintain linear operation, the MOSFET must be kept in the active saturation region. This means that 2 to 3 volts is usually needed before the MOSFET will begin to conduct. This is a problem for low voltage, low dropout regulators where you're down around 2, 3, 4 volts, but it's no problem with our very high drain voltage as a source for the regulated control voltage. The follower regulator is stable and it can drive a lot of current to the load. Without active feedback in a closed loop system, the regulation will not perfectly mirror our control voltage at the gate, but it will be pretty good and hopefully better than the Heathkit tube regulator. So that simple high voltage follower regulator schematic I showed before, that will work, but bad things happen instantly should you accidentally short the output. It's fine for internal fixed supplies like for perhaps a screen grid of a transmitter or a VFO regulator, maybe with an ARC5 transmitter or a DX40. But for a bench supply, we need more protection. A fuse simply is not fast enough to protect a MOSFET. MOSFETs are not forgiving like tubes are. The gate terminal is sensitive to voltages in respect to the source above plus or minus 15 or plus or minus 20 volts, depending on the device. So we need to protect the gate to source with a zener of maybe 12 to 15 volts DC, a 1 or a 2 watt zener. But even so, with a short, the fuse is going to go, but probably not after you hear a pop, see some smoke, destroy the MOSFET, and perhaps destroy the entire zener stack. So we will need some fast short circuit overcurrent protection. These protection circuits can get quite elegant, and many are on the supply side before the MOSFET or the pass transistor device. But I prefer protection on the load side. The idea is simple. Use a series sense resistor that's sized to produce a voltage drop at some target overcurrent, and use this voltage to protect the MOSFET. An ordinary NPN transistor will begin to turn on between 0.3 and 0.5 volts. So Q2 turns on, and it starts to short out the path between the gate and the source of the MOSFET. Thus, it begins to shut down the MOSFET from conducting. Yes, there's a price. If we were drawing 200 milliamps through a 10 ohm sense resistor, there would be a 2 volt voltage drop. 75 milliamps in a 6.8 ohm resistor, we get about a half a volt drop. It's a penalty, but not a bad penalty considering we're running 200 to 400 volts of output. The NPN transistor is floating, by the way, so it doesn't need to be a high voltage device. But do look for a small, fast power transistor with decent voltage specs. The BD139 or the MJE 340 transistors have reasonably high VCEO. They're high current gain devices. Those are good choices. In overcurrent protection mode, expect dissipation because absolute shutdown to cutoff is not guaranteed. We should have pretty good regulation. Operating the MOSFET in its linear region means it will dissipate significant power as heat. A properly sized heatsink is mandatory. We'll have to make sure that the MOSFET operates in its SOA, or safe operating area, with the heatsink. And don't forget about derating. Let's talk about the power supply front end. Before regulating, we first have to make some serious high voltage. How high do you want to go? For most QRP 1 and 2 tube transmitters, small power amplifiers, modulators, headphone amplifiers, regulating pentode screens, maybe 0 to 350 volts at 25 to 50 milliamps is sufficient. But let's at least try to emulate the Heathkit and try for 0 to 450 volts at say 75 to 100 milliamps. And we want to be able to supply full current over that range. This directly drives the specifications on your power transformer. For instance, 450 volts out at 100 milliamps, that's 45 volt amps. So probably we need to go for a 60 to 75 volt amp transformer. The upfront power supply can be conventional, or bridge full wave off the secondary, or some kind of voltage multiplier scheme. Voltage multipliers need a little bit more headroom in capacity, and they're very dependent on the filter capacitors that you select. I found an old surplus isolation transformer. It's basically a 115 in, 115 out volt isolation transformer with a 0.87 amp winding. So that comes out to around 100 volt amps. That's a pretty big transformer. The size and secondary rating will limit the current available, of course, because I will have to use a voltage multiplier. We'll see what I can actually accomplish with such a transformer using it in a voltage multiplier circuit. This should be interesting. This is a clever full-wave voltage quadrupler circuit. Basically, that's 120 volts because, remember, our 115 is actually going to be 120, times 1.414, that's V peak, times 4, so we could generate as much as 670 volts DC. There's going to be some high voltage here, right? We're looking for our 0 to 450 target range on the output. This is going to be fun. Of course, it's going to be a little bit dangerous. I have to tell you that this project presents some serious high voltage, Don't attempt this type of project without experience, high voltage precautions, and plenty of care. And this project is experimental. There's no guarantee of success, and the schematics are preliminary. As with all circuits on my channel, we work out the issues as we go. The current limiter is quite primitive, but I'll have a little more on this in the next video when we start to actually test the circuit. Remember to respect the worst-case power dissipation on the transistor. If you have a 35-watt transistor, you may think you're okay, but because of the way that these MOSFETs are designed, you might want to use 2 transistors instead of just 1. At worst case, which is the entire 450 volts, at 100 milliamps, we're talking 45 watts of dissipation on the device. So I probably will end up using 2 transistors, a couple of TO220s if necessary. Doubling up these transistors, you can usually just use a pair of 1K gate resistors and they will share the load. Good heat sinking practice and a massive heat sink are probably requirements with this project. A heatsink fan is not out of the question. And again, metering is needed. Let's take a look at some typical parts for our high voltage variable regulated power supply.
So this mess of parts is just kind of a reminder of the things that you should be looking for when you want to build a power supply like this. I see a couple of meters. These could be digital or analog. These are low-cost analog meters. That's going to make the power supply a lot more useful to you on the bench. There's a chassis here. I expect this project to be inside a box similar to the Heathkit box, something that's completely enclosed. If you do enclose the project with an onboard chassis or a plate, I think I'm going to build on a plate that has standoffs. Perhaps it will be cantilevered off the front as one unit that goes into the box. And if you do have an onboard heatsink or an internal heatsink, you may need a fan. If it's external, you probably won't. This project, it's going to use an IEC cord, so you need a cord inlet. You could buy an inlet or get one off an old ATX power supply. Speaking of ATX power supplies, I've scavenged a few parts. These can be useful for mounting transistors. Sometimes there's useful diodes and bridges, capacitors you can use off these old supplies. A lot of these insulating materials are reusable. Here's your high-value Zener diodes. These are actually 2-watt Zeners, 82-volt 2-watt Zeners. 1 watts are fine. I bought some IRFB G30s, which are a little bit of an upgrade from the 20s, but the 20s should work as well for the high-voltage FET, MOSFET. Sometimes you will find high-voltage FETs and transistors that you can use from the ATX power supplies as well. You can certainly find bipolar transistors off them that you can use. Some type of connection system, switches, a good quality 2-watt potentiometer for your voltage set control. And don't forget the little things like knobs and fuse holder, and you'll need various 1 and 2 watt resistors that you can order. So this is a good spread. Beside the transformers, here's some other parts that you need to collect to get started on the project. Let's talk about the transformers. If you're just making a smaller supply that's perhaps 0 to 250 volts for screen grid or low power transmitter type situations, you can probably get away with a small transformer like this. This is probably a 25 volt amp transformer, this kind of size. If you want to do the full capability of maybe 100 milliamps up at 400 volts, you're going to need something like this. This is like a 100 watt class transformer. Pretty heavy stuff. So your transformer is going to look something like this. It's going to be in between these two. You might also use a control transformer. I like control transformers because they're well insulated and well marked. And a lot of them are made specifically to transition voltages off the line. So don't be afraid to use a control transformer. Again, I'm going to be using an isolation transformer and a voltage multiplier So that's the way that's going. Also, I have selected a chassis. This is what the box is going to look like for the project. And again, I intend to cantilever a plate off the front panel and build everything basically on standoffs. So the entire assembly will be self-contained outside the box, and then we just slip it into the box and connect up a couple wires in the back, and that should be it. If you do build something into an enclosure, you have to make sure you can still service and get at the parts, and don't paint yourself into a corner. Anyway, next time we'll start to work with some of the electronics, get this thing breadboarded, and we'll see if we can get control. I hope you guys are enjoying this project. This is going to make a useful bench instrument, a variable voltage regulated high voltage power supply.